Hey guys, Simon here. So I'm gonna do something a little different again today, seeing as I haven't done something for a while. Um, I'm going to be showing you guys some analysis, I guess some reverse engineering, some threat analysis basically, um, locating interesting details within payloads, things that will lead you back to attackers, and those such things. If you guys can see here, it's just a bunch of tools. These are just a few you can use. Believe me, there are a lot more. I'm using the Threat Pursuit virtual machine, which, if you don't know, is basically a malware analysis virtual machine created by FireEye, a very good incident response company and malware analysis company. But yeah, so I have basically two demo payloads that over here that I'll be using for this, payload and Trojan. So you can see there are two next to each. There's payload crypted, and payload patched. Okay, cool. So let's just do this all for you here so you can see. I'll open up .NET Reactor. So first we're going to take payload. We'll protect this. Okay, cool. So we have over here encrypted. We'll crypt the Trojan. We can open up Patcher. Now the reason I'm not doing it all on all of them is just so there is a bit of variation for you guys to see. So we're going to take the patcher on payload. We'll do a bit of changing of the crypting settings here. This one will take a little bit longer to do. Okay, cool. So now that this is finally finished, we have our payload patched because it came from the .NET patcher, just so we can keep a record of what's going on. Okay, cool. And then lastly, we'll use Phoenix Protector to protect our Trojan file. And we have saved our payload, so we can open our folder here. Oh my god. And we have Trojan protected. Great stuff. Now we'll start off with some easy things. PEIB, which is basically executable identifier. So basically, it's just going to identify the language, the files we give it. So we'll pass it payload. As we can see, it's a Visual C# or basic.NET file. And it'll say Trojan, and you can see it's the same with different entry points. So you can see it's not the same file, but I'm using similar languages just to make this intro fairly easy for new people. We can take protection ID, which is basically a great little program that will search for whatever protection products have been used on a program. So I'm going to pass it payload crypted. If you remember, it was crypted with the .NET Reactor. So I'll throw that in here. And as we can see, .NET Reactor was detected as the program's protector. We can see it's a .NET compiler, so it was the VB.NET. We'll throw in the crypted Trojan. Again, we can see it's a .NET Reactor. Let's see what else we can see here. We can see some version info of the file, which we can check from a couple other things that we'll go through. It tells us it's a 32-bit, so it's compatible on both types of systems, 32-bit and 64-bit architecture. Let's go with payload patched. And it has thrown out a couple things. .NET Reactor, .Fuscator, Confuser, Goliath.NET Obfuscator, and .NET Obfuscator. Now, the reason for this is because the .NET Patcher, if you guys remember, let me just show you again, because of this obfuscator. Now, because of this obfuscator option, it gives us a lot of extra things that we can use to crypt our file, which is why it's basically given us that it's been obfuscated or crypted by 5 different things, because essentially it has. And then we can put in the Trojan protected from the Phoenix protector. And as you can see here, .NET Reactor and the Phoenix protector has been detected. The reason .NET Reactor shows up all the time is because it's a pretty stock standard in terms of .NET scripting. It's usually a base that is used. But yeah, so we can move on from here. The next thing I'm going to be using is PE Studio. Great little program. Cool. So I'm going to, first of all, toss in let's put in the payload patched. So what it's going to do is basically load up a bunch of information about the file, tell us some properties, MD5 hashes, SHA-256 hashes, the first bytes, the first text, the file size, the entropy, hash signature, all those good things. We can check when it was compiled. So mine was compiled today, as I'm sure you guys can see. It'll show us some DOS header information, which is basically entropy, file ratio, hashes again. It will load up some file headers for us, optional headers that could have been passed to it, showing if it's a GUI program, if it's terminal server aware, control flow guard, all those good things. It'll show us directories, so export tables, import names, resources, the size it takes up, the location address within it, whether it's a text section, resource section, relock section. It's still loading up a couple things here. PE Studio puts it through string checks, TLS callbacks, exceptions, exports, imports, libraries. Though because it has been encrypted, it is trying to just gather whatever information it can as well as it can. So we'll just give it a couple seconds. Shows us the manifest file, so the requested execution level, meaning whether it's going to ask for admin privileges when it's launched or not. This does not, so it would get launched as a regular user. We can check the version of the file, which was 0.1.3 when it was created, or as specified by the payload folder. Okay, cool. So we've gotten a couple extra things back here. We have libraries, the .NET Runtime Execution Engine libraries that were imported. So the payload has imported mscore.dll to run. It uses the core exe main to run as an implicit import. We have the relocations, resources, and strings. Now this is very interesting over here, because this will always give us a lot of good information that as an analyst or a malware researcher would be very useful to us in terms of finding the adversary. So as you can see here, it has a couple strings. Take note, it's 19,844 strings. We can sort this out here nicely. We'll bring up the blacklisting strings. So what would normally be picked up by an antivirus, things like find window extension, empty the recycle bin, get the async key state, block input from the keyboard, hooking into Windows, getting environments, variables, creating remote threads and processes, all those things that you wouldn't want happening in the background of your system. Now we can take hints to look at things that we should be looking at: send, encrypt, write, start, copy, replace, control. These are all things that the payload would probably be able to do as utilities. So it can send information, it can encrypt information, it can write files, it can start applications, copy things, replace things, control things. For URL patterns, this is what it's giving, so as a fallback address. So obviously there is no IP of 11.0.0.0, and just for your guys's, I suppose, information, the payloads have been built to 127.0.0.1 localhost. This obviously is not the localhost. So our callback address has been encrypted, which would make it harder to find an adversary, but not impossible. There are ways to do it. Instead of checking something like this, we could use something like Wireshark or FakeNet, which would basically throw up a proxy, run the payload, and try and get it to connect back to where it needs to go, which would then register the IP address for us. I'm not going to do that today though. Sorry guys, I didn't install Wireshark in this machine, and I didn't have FakeNet running. This is just going to be slightly introductory, and it's already getting a little long. So yeah, we'll save that for another one. So I will open it up again. This time I'm going to put through the regular payload and let that do its thing. What I want you guys to remember is the strings amount for the patched payload was what, 19,800 something, about 20,000 odd strings. Once this loads, I just want to show you the difference between the two. There we go. Strings 1,750. If we look for the blacklisted strings, we have 27 of them, giving us a lot more information this time, as opposed to we had 14 blacklisted things from the patched one, and here we can see a lot more information. It's looking for antiviruses, it's looking for processes and hardware information, it's getting windows, it's enumerating windows, it's hooking windows, it's getting storage, it's looking for shells, it's mapping keyboards, it is literally doing all those things we would want it to. It's checking hints, 86 hints, whereas we had 20 last time, replacing, controlling, connecting, scheduling tasks for auto run. It has, here we go, for URL pattern, we have our callback address. Yes, we do have these as well, that's payload functions built in. Here we have looking for video controllers. We have logging the file in a remote directory. So when it's run, that would be deleted and it would start running from here. We have the stub file. We have a bunch of DLLs that it's loading. If we look over here for sections, we see a lot more information, the virtual address, the raw size. The libraries obviously only need the one to do its thing. But yeah, so now we've seen the difference between those. Let's take a look at the Trojan protected with Phoenix protector, and then we'll look at the regular Trojan and then go through the .NET React files. So because this was a protected file, I'm going to say it may take an extra minute or two just to read all the information. So I guess not. So we have strings here for the protected one is 1295. If we're looking through it, we have 14 blacklisted, 22 hints. Let's look at the hints first. We have control process start. A lot of them are quite similar. The URI pattern looks like it's going quite similar as well. We have over here, obviously, files that would be rewritten to. Let's check out the blacklist. Again, download file, virtual protection, all those things. But looking down over here, it doesn't actually give us the callback URL, which is a good thing for the attacker, not so much for the analysts. But again, we can use something like FakeNet or Wireshark to get those IPs. We can also get the original file name. Seeing as it doesn't really change a lot, that's not anything that we need to worry about. We have indicators over here, which I guess I didn't go through the last one, but we will do. It shows us a URL pattern count, file counts, DOS messages, obfuscation, checksums, blacklisting, yeah, a bunch of things that we would probably want to take note of. Level 1 obviously being the worst. But yeah, let's check out the regular Trojan this time. I don't think it's going to take super long to load up, seeing as the last one didn't. So string difference between the Phoenix Protect and the regular wasn't super different, but you can see here without decrypting, there's automatically more hints. We have the callback address and a lot of extra information that the analysts weren't getting the first time. If we check out our blacklist, it's fairly the same as the first. We can check out the indicators again, same-ish data. URL count 2 instead of 1. It gives us the actual callback address this time again. Yeah, so let's quickly check out the payload encrypted, and then I'll take you through one other program before we finish off this video. So the payload encrypted file, if you guys remember, was done by the .NET Reactor. I'm not going to show you the .NET Reactor of the Trojan, obviously, because that's all fairly similar-ish looking information, and I just wanted to give you guys sort of an example of where to be looking for these things. Strings 2047, where the original one was 17, and the patcher was what, 19,000. So obviously the patcher out of these obfuscators would be the best one. But looking at the hints, it is loading up a lot. So we have obviously the utilities the payload would use, looking at the URI patterns. We don't have the actual fallback address. We can look through the blacklist and sending information, scanning keyboards, hooking windows, executing processes, obviously all bad things that we would want to watch for. We get the entry points of the files and such. We can see whether it's executable, whether there are writable values within it. The entropy of crypting that has happened, DOS stub. We can check obviously file headers to cross-reference, see if they match with what the legitimate files could be. If say this was an installer for what VLC media player, it would have certain headers, certain hashes that we would hope would match with the file that we have. Okay, cool. So the last thing I'm going to show you guys before we head off is dnspy. So dnspy is basically a source viewer modifier for C# and VB.NET files. So in this case, it should work for us. In future videos, I will probably go through IDA and GHydra, and maybe I'll go through Extreme Dumper this video, otherwise I'll do it in the next one. But if we look over here, we get dnspy. Let's close out all of these, and we'll throw in the regular payload. So it'll start going to work, decompiling it for us. So we can basically see the information. We can see it's loaded up ms core lib, which is the runtime DLL that the file imports for us, or for itself to be able to run. So we can open up the file here. We can check the references within it. We can check resources within it. Which is basically just stub resources in the file. We can check module info, other code that would be inside. So obviously the stub would invoke some anti-task manager things. The task manager would have closed had the payload been run, and it wouldn't have been able to open again because of these. We have window enabling, window enumeration. We have the protection threads, which is basically just parts within the file that have been encrypted. We have the Chrome function, which would then be stealing Chrome information. We have RDP stealing, USB spreading, virus. The virus total function over here is also quite clever. It basically would stop the file or the user's computer from being able to browse to virus total. So anytime they enter that into a browser, it would automatically just shut down the browser. We can check out, and as you can see, a couple more things have loaded, because as we go through resources, it decompiles it and it pulls in the resources that we need to be able to be used, which means it is somewhat dangerous-ish to be going through this on a regular machine if you don't know what you're doing, because you could basically execute code from a malicious payload that you wouldn't want to. So we can right click on the file up here. We can go to the entry point. So it would basically take us into where the application itself starts. As you can see here, it would enable a browsable state for itself. It would call in some implementation methods, and this internal static void main would be the starting of the application. So if we go down here to run, we click on run, it would basically take us to the next part of the file, where it starts to pull up the command line in the background to start calling events, basically creating the application model, which means it's going to delete itself. So it would delete the payload here off the desktop. It would move it to a hidden specified location, and then it would start running from there. We can see here network available, event adapter. So basically it's checking whether there is internet available for the payload to be doing its things. And just so we don't take super long here. I will show you guys a lot more next video, but yeah, I don't want this one to end up going for way too long. So I'm going to close all these out quickly, and we're going to open up the regular Trojan. And from the start, we're going to go to the entry point. Over here, it would start to look for the server. It would try to connect to the server as either user or admin, whatever we have told it to. We can the run function. It would start to loop through to start deleting user cookies from the browser. To start getting us to relog back into accounts so you can steal information, passwords. Here, okay, well, seeing as this video is going to start to get really long really soon, I'm probably going to end it here, but you guys now have a basic idea of how to find out the scripting language a malicious file has been written in, how to search for malicious strings within PE Studio in headers, how you can start to decompile source code to try and find interesting artifacts within it. Let's see, before we go, if I can show you guys process dumper, so we can get our debug privilege. So this would basically act as a, I guess, semi-debugger. Let's go with payload. There we go. We can see payload is running. So let's go with view modules. So we can see all the modules that payload is basically running right now. It's sort of where they are. It's pulling up assembly from runtime files. It is dropping some keys. We have other dependencies being called. So we can see what in real time what modules are being called, what modules are being run, basically dumping what it's doing. We can dump the selected process, then save it to desktop protected just because it's over here. We can check out the dumps of the file, and we can see the dump has basically given us the stub. It's starting to pull out dependencies and basically give us the inner structure of this file. We can see that it's calling out a bunch of different DLLs and all other files that are within its used to be run. So in PE Studio, let's open this up here again real quick. So stub was the internal name of the file, which we can see is here. It's the original file that the RATS builder obviously uses when it builds its payloads. So essentially what these were processes that have been called from, obviously the various parts within the file, the resource information, the implementation information, and basically everything inside of it. So yeah, I hope you guys have enjoyed this video. I know it's been really long. Obviously there's a lot within the umbrella of reverse engineering, of malware analysis, of kind of just checking things out. And I encourage you to do it, but please, again, do things in a virtual machine, do them on a computer machine that is not your base, because if you don't know what you're doing, a lot of the time things can go wrong. You can run files by accident, you can execute processes by accident. These obviously are just wrap payloads, so without a central point for them to connect back to, they don't do much. But when you are doing analysis on something like ransomware, the smallest mistake can have that ransomware execute and screw up the entire machine you're on, which isn't an issue if you have virtual machines with snapshots that you can obviously just roll back on. But yeah, you need to remember to do that. Use virtual machines, take snapshots, protect yourself, protect your data, protect everything around you, and yeah, just keep yourself safe. But anyway, I'm out. If you'd like this, like, comment, subscribe, let me know. And yeah, I'll be back again to do a bit more malware analysis, to do a bit more coding, to do a bit more development, to check a couple more cool things out. But yeah, this is Silence, and I'm out.